Well, that's.
Should we get a?
How many were supposed to get?
I would grab like 5.
Like 5 people going to do?
Well, there's 2 pieces per 2. Oh, sorry. Yeah, they're cut in half. Okay, so grab 10. Grab 11.
Okay.
Grab 12.
Okay.
We can pass them around as if you run out. So just grab 7 for that. Just grab a bunch. If you run out, you can always get more. Okay, good morning, everyone. Welcome to our first day of project presentations. We have a very tight schedule in order to fit all 23 of you into 2 days. We have to kind of keep the time list that I put up there. So if you know who you are after, I would start preparing to go as that person is wrapping up. I have all your presentations on this computer, so I'll go ahead and drive. But just make sure that you're ready to pop up here when your time is up. Those of you who are showing creative projects, I've given you 5 minutes to sort of talk about to show off and talk about your projects. Those of you who are doing formal presentations have 6 minutes plus 2 minutes of questions. I will cut you off at 8 minutes and kick you off here if you don't finish by then. Now, keep in mind that I am evaluating these presentations. This rubric was online, so you should have an idea of what I'm looking for in your presentations. I'll also be collecting all of your evaluations for each other. That is your attendance extra credit for today, but it also will help me in sort of assigning a grade for the evaluation of the projects. Any questions? Crystal clear. Okay, Sebastian, you're up.
All right. I planned for 8 minutes, so I'm gonna go as fast.
Go as fast as you can.
Okay.
So you can just use the
side thing.
side things. Yeah, let's actually give you the tools to succeed here. Left, right, and then a laser pointer on the top there. Push that button, everything will explode.
Oh dear.
No pressure.
And red. All right, hey guys. I'm Sebastian Kaiser, and my project is a mission to Mars. So, go to Mars. I have 4 main phases. 1, setting up a base on the Martian moons of Phobos and Deimos, using robots to manage robots on Mars. Yeah. The second phase, putting humans on Mars to arrive near the base and then begin exploring and conducting research. And this involves multiple waves of scientists coming through and replacing those before them. Third phase is the colonization of Mars. So once they have a big enough base set up, then they can have more people come in and begin habitating the planet. And the fourth phase is the terraforming of Mars. And this will include inducing artificial greenhouse gases to melt the carbon dioxide in the polar ice caps. And once the planet starts to warm up, we can probably start to plant plants and introduce oxygen and stuff like that. So here's just a picture of Phobos and Deimos. Just some little information about them. Phobos is the closest one to Mars and is also the largest, while Deimos is farther away and is the smaller. Phobos has a rotation speed around Mars of 3 times a day. Looks like it was cut off there. And Deimos has a nearly synchronous orbit with a rotation period of a day and 6 minutes. No, 6 hours. My bad. So some pros to using Phobos as a moon instead include its proximity, while Deimos has a sweet spot near its Arctic Circle where it receives 10 hours of continuous sunlight during the Martian summer. And this would be a good base for scientists to get direct line of sight with Earth and Mars as well. So why go to Phobos or Deimos? So first reason is that there's an incredibly small lag time between between scientists or between the scientists and the rovers. So the lag time between the moons is less than like a tenth of a second, while from Earth to Mars it's 4 to 24 minutes or so, averaging to about 25 minutes like both ways, where it can have a range of 8 to 44 minutes. So you can see there's a clear advantage there where you can have multiple, or you can have a robot move a lot faster than you can today, since they go so slowly, since there's such big talk time. And they would also be able to accurately position habitat modules on the planet and other equipment. They also have a much weaker gravity, and so it's cheaper and easier to launch rockets from, and key technologies can be proven to work on Mars using such life support systems like air recycling and water recycling, as well as biomedical technology to protect against radiation and microgravity. They also can conduct research on the moons themselves, such as determining the internal composition, or looking at subsurface samples, or searching for pieces of asteroids, comets, or maybe Mars itself, which could hold potential answers or clues to whether it had life or not. And it also served as a biobarrier before transporting to Mars. Transporting from Mars to Earth, like samples and such, so not to contaminate the samples or not to contaminate Earth if there was something contaminated. All right, so what's going on Mars at this point? So as written out in Robert N. Zubrin's plan called Mars Direct, he specifies that a rocket sent to Mars would include a habitation module, nuclear reactor, chemicals or compressors, chemical processor, and liquid hydrogen to produce fuel, and rovers to carry out tasks, extra food and life support, and an Earth return vehicle and utility truck, which utilize liquid methane and oxygen as a propulsion means. So they would use in situ resource utilization, which means using resources from the source and producing them there, so they don't have to bring them over from Earth. And this would be done using the compressors, taking carbon dioxide from the air and the hydrogen from Earth to produce methane and water. And they would use a chemical processor to break down the water into hydrogen and oxygen, and then the hydrogen would be reinserted into the cycle, and it would start anew. And they could also produce extra oxygen or water if needs be. So the second stage, having humans actually land on Mars, the crews would they would go near the site where the previous thing landed, and they would have another rocket sent over, identical to the first, landing around 800 kilometers away, so that they'd be able to reach it with a utility truck, which has a range of 1,000 kilometers or so, in case something goes wrong. They would use this truck to drive around and explore the surface, searching for exploitable water ice to find water from, and then they could live on the truck for multiple days at a time. They would also use inflatable greenhouses to grow or experiment with food, because we don't know how Martian plants taste yet. We would install UV protection shielding to protect from the harmful rays. And after every year and a half or so, more scientists would be sent over, and the process would continue, allowing them to either expand across the Martian surface more, or expand a current base to prepare for future settlers. All right, so here's a picture from Mars Direct. This is the spaceship they landed on, including the Earth return vehicle. This is the habitation module, and then this is a little greenhouse right there. And here's some more pictures from this book I read. Just there's like a truck and then some walking around and experiments and stuff. Anyway, so phase 3, the colonization begins. With advances in propulsion, we'll be able to send multiple scientists and people at a time, and these would be trained scientists, and they'd be able to take over for the astronauts. But they would also need a source of income, since there's a lot of money invested into this project, so they'll need something to export back to Earth. So because of like the tools they'll need from Earth until factories are made and whatnot. So they could export materials such as silver better, which is proven or shown to be the only that silver better to make it profitable. So they could either get this from mining on Mars or from the local asteroid belt. Oh shit. Okay. All right. So using Mars as a waypoint, they could also get deuterium, which is an isotope of hydrogen and used for nuclear fusion reactors. And this is 5 times more common on Mars than on Earth. So it'd be really profitable. Here's a picture. Yeah. And so how to get to and from Mars. There are these thing called cyclers. You can use them to go into continuous orbits around Mars and Earth using the gravitational pulls of the planets. One-way journey would take 6 months, and to go the other way around would be 20, so you need one going each way. Only problems would be the velocities needed to catch up with these things. And then here's what one could look like. And the final phase, terraforming the red planet, using artificial greenhouse gases called CFC. You would start to heat up the planet and melt the polar ice caps, inducing global warming. After about 40 years, carbon dioxide would eliminate the need for pressure suits, using only scuba masks. And then plants could be grown outside eventually. The permafrost in the soil would melt and water would start to flow. After maybe 100 years, rain would fall, allowing plants to grow on their own. And then the increase in oxygen in the atmosphere would eventually allow people to live outside. And here's a picture from an artist where you can see this is where it starts. There's habitation modules here, and then it continues where there's eventually pines and grass and some guy chilling here. Yeah. Any questions?
Yeah, 1 minute for questions.
What about ethical issues of this? The whole idea of it.
What kind of ethical issues?
Colonizing and setting up.
Well, I mean, humans from the beginning of our time have always been explorers and going out to different places to conquer, or not necessarily conquer, but just settling places, the settling of America, there's already indigenous population there. It everyone, it's just human nature you just want to go out and explore more. And we don't know if there's any life necessarily on Mars. So, I mean, if there were, then that might produce ethical dilemmas for terraforming the planet, especially. Because then if we would do that, then it would essentially kill everything on there. But since there's no life as we know it there, I guess the other ethical dilemma would be humans staying there for the rest of their lives, but it would be personal choice. You have a question?
I don't know if you already covered this, but do you have a rough estimation of how much it would cost?
No. Well, there's been some estimates. For example, the Obama administration has estimated that not necessarily the whole caboodle, but maybe the first few steps would take $200 to $500 billion. But those are just
Much less.
estimates.
About 80 to 100 billion dollars.
Oh, really?
Cheaper than a war, right?
Yeah, probably. Wait, 80 to 100?
Yeah.
Oh, okay. Yeah, I think I read that too. Maybe, I think there were higher estimates at the time.
Okay, thank you, Sebastian. Okay, so Trang's going to be doing a presentation. You've got 6 minutes, and I'll give you a warning.
All right. Good morning, everyone. My name is Trang. I am going to be presenting a creative project today, and it's going to be on astrobiology and astrology. So by show of hands, do you guys ever read up on your horoscopes or astrology? Yeah, okay, awesome. So first off, I'm going to start off with some definitions and the objective of my creative project. So astrobiology, as you guys know, is the study of finding life beyond Earth. Astrology is the study of movements by celestial bodies, which then is interpreted to have effects on human affairs. And both of them are related through all the matter and space that exists in today's universe. So some creative decisions include the interactive engagement between the project and you guys, and that will be later on. And then the goal of this project is to examine the validity between the two different studies around the focus of celestial bodies. So a little background on astrology. It began somewhere between 5,000 to 6,000 years ago, also known as the early to middle Bronze Age. It started off as tradition, but then it took part in studies such as medicine, politics, and such. Early civilizations were aware of the movements and cycles of these bodies in the sky, and they were curious, of course, so they started observing and documenting all of those. And so naturally, due to this process, ideas and concepts were formed, questions about how the bodies got up in the sky, what do they mean, and then how does it apply to us human beings. So some functions of astrology. Today I'm going to focus on Western astrology, and there are 12 main astrological signs. So in order, they are Aries, Taurus, which I am, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. So these signs are determined by two factors, the Earth's rotation around the sun and the Earth's rotation around its own axis. So from these signs, you can derive a diverse and a huge array of characteristics that represent your personality, your attitude, your intelligence, and they also foretell events in your life, such as your personal life, your love life, school life. So this is an example of a typical astrological sign. The dates on the left are the ranges. If your birth date falls between those dates, then you are the according sign. There's symbols, and then just an extra keyword that apply to your sign. And then this is an example of an astrological chart. As you guys can see, each sign is assigned an astrological element and a planetary ruler. All signs participate in, are associated with all the planets, and they participate in every house. But these are the most strong elements and planets that apply to your sign. So I'm gonna go back to, and there's one more. And then this is a super complicated birth chart. This takes the birth date, your birth time, your location. This is just one of them. So you can see that there's many symbols and numbers and letters. But I'm gonna go back to this. If you guys wanna find your sign, go ahead and take a few seconds to do that. I'm born on April 21st, so I'm a Taurus. So yeah, everyone have their sign? Okay, awesome. So before we start, I'm going to explain planetary rulers and houses. They're basically aspects of your life. Like I said, every sign participates with every ruler and house. So like I said, I'm a Taurus, so I'm governed by Venus, and I belong to the second house. And then okay. So this is the current night sky of June 1st at 2:30 p.m. If you guys remember, this is from our first lab. Go ahead. So these are the first 6 signs. I pieced together some readings based on your signs from the night sky. So if you see your sign, go ahead and take a minute or 30 seconds to read it really quick. So yeah, these are the first signs in order: Aries, Taurus, Gemini, Cancer, Leo, and Virgo. And these are the last 6: Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. And then there's one more slide, and it talks about the validity. Astrology prompted famous scientists such as Kepler, Aristotle, and Copernicus to further investigate and examine other fields of study like astronomy. The patterns in nature were no coincidence to these early scientists, and they have had impacts in other subjects as well, such as philosophy, theology, and religion. And what I want to ask you guys is, do you think it's a learned discipline or a practical art? Yeah, that's my creative project.
Questions?
That was really fast.
What do you mean by houses?
So houses, they belong in Zodiacs. So houses are like aspects of your life. they have to do with your birth location, your birth date, and stuff like that. But the one I showed you is very general, very broad. Yeah, because I'm sure everyone's varies. So yeah.
Does yours match up with your personality or life?
Yeah, I would like to think so because I'm a Taurus, and they said that they're very stubborn and I'm very hard-headed. So you know, sometimes it's true.
Yeah.
Yeah.
Any last quick questions? So you mentioned extremely briefly a study that shows that there's no correlation between.
Yeah, so
Astrological
one of my
signs, so-
primary sources is done by this researcher called Hartman. He did an experiment with 4,000 middle-aged men and 11,000 young adults, and he took samples of their birth dates, times, location, etc., and he found that there was no correlation. So, yeah, I mean, I don't think anything in this world is 100%. You know, the constant is flex, but I think it's subjective when it comes to studies like astrology. So.
Okay, thank you.
Thanks.
Okay. All right, Tatiana's got a 5-minute creative component presentation. You want me to show your picture? Or do you have it up here? Okay, you have it up here. You want me to show your picture, or do you?
I have it, but yeah, sure. It's the same. Have to show it. So my creative component is basically a board game. It looks like this. Same thing up there. Kind of hard to explain, but I'll just it.
You want me to hold it?
Yeah, pretty fast. Okay, so the main concept of this game is that the game teaches the components of planets and the necessary components for life. The game is about the creation of planets within the solar system and life on these planets. It is a mixture of a board game and a card game that uses a point system to determine habitability of a planet, while players build planets and race to reach the habitable zone. So here's the start. This is the habitable zone. This is the sun. There's little lines here. You can't see them, I don't think, but they're supposed to signify kind of the orbits of the actual planets that we have. I only have enough room to get up to Neptune, but these little colored spots say that, for example, with Neptune, you're caught in its orbit, so you move forward one space, and then freeze is you lose a turn. Satellite, you draw an extra card. Uranus, again, solar flare, you recycle all your cards. So basically, the objective of the game is to build a planet with the optimal levels of and elements for life. You collect as many points from different elements of life in order to create the prime planet for life. Points are totaled at the end of the game to determine who has the most developed form of life on their planet. Points are designated to a different card that shows the features. So I actually have the cards, but so the way you play is each player is dealt 5 cards. So each time, so you're only allowed 5 cards in your hand at a time. 1 second. You use dice to determine who goes first, you know, the typical roll, whoever gets highest. And then each player begins with a cold, barren planet, much like Mars, or just kind of like one planetesimal, which is determined by a certain mass. I'm not sure if you guys can all see, but these like little star things are the little like movers, you know, things like that. Yeah, so they're little like paper stars. Each person, so these little panels, you put your notepad because throughout the game, you will be building a planet. So you need to keep track of how many points you have and how habitable your planet is so far. As you progress, you can attack other players. So the different cards, for example, each time, I think you have to pull those down. But each time you roll the dice, you pick a card, you draw a card. So after you draw the card will say something. For example, if I draw this card, it's evolution, which means it fast forwards time for that one planet for 2 turns. So each round, so if I started, and once it's my turn again, it's been 0.5 billion years. So, you know, time keeps progressing, which counts up to how your life evolves. And during the whole game, you're only creating a planet. Once you get to the habitable zone, which is the end, that's when you can actually tally up your points for life. So there's 3 ways to win. The first way is you reach the habitable zone first, and then you have the most civilized life or most evolved life. The second way is if you're still all the way like back here, or I guess, yeah, back here, and somebody already reached the habitable zone, a timer starts. So you have 9 rounds to end, which is 4.5 billion years, which is like when, like now of Earth, I guess. So yeah, that's when the timer starts, and you have 4.5 billion years to reach the habitable zone and produce life. Or if you're so far behind, you can just start destroying planets. So there are different cards that. Oh, okay. So there are different cards that actually like have you destroy planets. So it's a bit complex, but there's a whole like the rules have all the explanation in it, and this basically connects to our class because it explains, like it teaches kind of what you need in a planet to create life and how that life like came about within a certain time limit of Earth. So
Okay, thank you. Any questions? One quick question? Yes.
So you're assigned a planet that you have to inhabit by the end of the game.
basically, or if you have no luck, because it depends on the cards. If you have no luck inhabiting, you just start destroying other people's planets. So it's like last man standing.
Okay, thank you very much. Okay, so Sanjeev is going to be giving a presentation. I'll give you a warning at 6 minutes.
All right, so I'm presenting the creative component of my project, and my name is Sanjeev, and I did interstellar nursery rhymes. So, all right, so basically my main project was about supernovas, because we learned about how supernovas influence the creation of like heavy metals and heavy elements, and how that in turn influences life on other planets, and how we need like heavy metals and heavy elements for radiation, which drives radiation inside the planet. So I mean, I did my entire project on that. So I was like, okay, well, I need to do something for my creative component. And I was just sitting and thinking, I was like, well, Twinkle, Twinkle, Little Star, that's a poem that's practically begging for someone to adapt it to this class. So I decided I would base my entire project off of that. So I was looking at it, and I was like, well, nursery rhymes have potential since we teach them to kids we read them to kids from a young age. They go to sleep listening to them. So let's make them educational, and they can learn about space and life in the universe from a young age. So I'm just going to read you a few of my poems. So this is the first one, just Twinkle, Twinkle, Little Star. So I have it right here in the book. So twinkle, twinkle, little star, fusion only goes so far. It will soon come to an end, running out of hydrogen, shrinking and collapsing star. Soon you'll go supernova. So I'm not much of a singer, but yeah, that's kind of the gist of my entire book. It has but I mean, kids will learn to appreciate the temporary status of stars. You know, they don't last forever. So I've separated my book into 3 sections. The first 2 poems are about collapsing stars. This one's called the Itsy Bitsy White Dwarf. So the Itsy Bitsy White Dwarf stole some solar mass, took material from a companion and didn't give it back. This raised its core temperature and fusion ran away, and the Itsy Bitsy White Dwarf exploded one fine day. So that was based off the Itsy Bitsy Spider. And the second part, so part 2 of my book, is it's based on solar system formation. So this one is called They're Clashing Colliding, and it's based on It's Raining, It's Pouring. I'm sure you guys all know that song, Man Bumped His Head, Went to Bed, and Wake Up in the Morning. So this poem's about how filaments combine. So when stars are in the making, we have molecular clouds, and sometimes supernovas will emit such a great shockwave that these filaments of molecular clouds will combine, and they can start to form stars. So that's what this poem's about. This one's called The Silicates. Oh, and here's They're Clashing Colliding. They're clashing, colliding, filaments combining, dust and gas accreting, mass stars are in the making. Right. And then this one's about how planets form through the congregation of silicates. Then I have 2 poems about radioactivity and isotopes, because supernovae are a huge source of these heavy elements. So I decided to include 2. You guys want to hear one, or?
Yes.
Okay. You want one inspired by Humpty Dumpty or Row, Row, Row Your Boat?
Both.
Okay. All right. The one inspired by Row, Row, Row Your Boat, it's called Flow, Flow Isotopes. Flow, flow isotopes through interstellar space, deposit on Earth and be a part of radioactive decay. And then the last one is called Iron 60, which is inspired by Humpty Dumpty, because Iron 60 is a pretty big result. It's emitted in huge quantities from supernovas, and we found it here on Earth. So let's see. Iron 60 found in the sea in larger numbers than there should be. All the smart scientists from near and afar found it had come from a supernova. Yeah. And that's the book. So thank you. Any questions?
Any questions?
So when are you publishing?
Yeah.
I didn't really have any plans, but I mean, I'm willing to sell this book if you want it.
First edition.
First edition, yeah. I'll sign it too.
Any other questions? Okay, thank you, Sandeep.
You want the?
Yes. Haha, I got it.
Make sure you get it signed.
No kidding. Daniel is not here. Okay. Oh yeah, you're here. Okay. Sorry. Did you didn't send me anything?
Yeah. You emailed.
Oh, sorry. The other Daniel. But yes, you have sent me. But the other Daniel's not here. But you're okay. Okay.
So I know.
You're up.
Oh.
Okay. So I just have the poem. That's it. The picture. Did you just send me a presentation?
Says exit from the bottom. If you scroll down to the bottom.
Well, that is Planetary, right?
Yeah. Do you have a slide as well?
Oh no.
Okay. That's all I need to know. Okay.
All right, so this is my project, and I did a poem, and it's about my whole project kind of thing was about volcanism, and so yeah, let me read you the poem. Volcanoes help us begin life on Earth. Plate tectonics provided a bit of girth. As one plate subducts under the lithosphere, the magma rises and turns it up a gear. Gases are released into the air as lava flows trickle down everywhere. Then up in the sky you see a plume. Don't worry though, it's not the day of doom. The creation of the oceans is a mystery, but perhaps volcanoes created them in their long history. It's a possibility with the outgassing its steam that it turned into oceans and streams. Volcanoes have the potential to cause catastrophes, hence geologists have come up with monitoring strategies. Only one problem, eruptions are unpredictable, although detecting seismic waves can give rise to a miracle. With technology reaching its pinnacle, the amount of damage can potentially be at a minimum. That's why monitoring is important now. No need for buts or how. Last but not least, volcanoes help our atmosphere with CO2, which allows the carbon cycle to be true. And in return, we get the greenhouse effects with making life on Earth perfect. So yeah, that's my poem. And then I created this background in this Photoshop-like program. So I just made a volcano with some lava and gas exploding, and gas coming out and lava blowing, exploding, erupting out. And so yeah, that's pretty much it. I mean, the whole thing was some of my articles were about monitoring, and so that's what kind of the seismic waves and monitoring kind of part of the poem came about, and then a lot of it was kind of general kind of things about volcanoes, such about the release of gases in the air, and yeah, that's about it.
questions? We've got a couple minutes. Yeah.
Then,
There were two Daniels, so Daniel Hernandez. Any questions about the project other than the person? Okay, can you tell me a little bit more about you mentioned that your sources were about monitoring. Can you talk a little bit more about
about the actual.
how the sources, the sources and how they connect to the phone?
Oh, so like, well, the article was about monitoring, and so then, the article showed about how the main thing was that there's like about 400. They studied like about 400 volcanoes in 16 different countries, active volcanoes, and so the whole point of it is that they're saying, well, almost 400 of them are unmonitored, and so. And like they're trying to, well, the volcanoes are very hard to predict, and so in seismic waves is one way they try to get like a sense of when it can erupt, because the magma causes like different changes on the outside of the volcano. So they use electronic meters kind of thing. And then there's also like satellites that measure from up top the surface and subsurface, and they're talking about how it's just important that they monitor the volcanoes because catastrophe can strike, and there's a lot of countries or cities that are really near volcanoes in the proximity of them, and they're unmonitored and just cause a lot of damage.
Okay, thank you, Daniel. Daniela? Did all my D's all at once.
Can you put up the slide that I sent?
Yes.
Okay. Hi guys. My project was on like the theory of evolution and how like Darwin came to that conclusion, and not only that, but just how a species in itself can evolve, and like how we can see that progression. And it's really easy to see with like the finches, which is why Darwin like was able to come up with his theory, and he was able to like analyze that whole situation. I originally was going to do like my project based off solely his journals, but I actually found a team of researchers that went and studied one specific island and one specific finch for 30 years, and so they were able to see for a pretty long like time span like how they changed according to like the droughts that happen and all those things. So I made like there's a thing called the Darwin's compass, which is just like the 4 basic finches, and then you kind of expand into subspecies from that. So like you have like this one, which is G. diffilis, which is this one, which is actually that one, and this one is like its name is like the sharp-beaked groundfinch, I think. And then these are also called like vampire finches because although most of them survive off a diet of like they'll feed on like nuts and other things like that. A subspecies of this one, which is like they're called vampire finches. They actually feed on like birds, like the buoys or whatever. I don't really know what they're called, but or bobbies. I don't know those birds that like sit on the ocean, but they'll actually eat those. Yeah. And then they'll actually eat those. And then you have, I actually don't know how to pronounce these, but it's this one. This is this one. And these are vegetarian finches, and so they survive off a diet of like
just leaves and buds and plants and things like that. Their beak is actually like pointed towards the end because they use it not as to like crack seeds, they use it more to manipulate their food and to like break up the bark so they can get under there and get whatever they want from under there. They'll eat occasionally caterpillars, but that's like rare. But usually they live in like montane forest areas because that's like the most trees and they usually stay there. This is this one, and this is actually the largest finch that exists on like the Galapagos Islands. It has the largest beak and it's like the largest body-wise. It's called the large ground finch, and then it's found in like the arid zones of like the Galapagos. And its large beak is used mainly to crack nuts. This is called the green warbler finch, and this one I actually wanted to paint in green, but like I couldn't find like the thing it's supposed to be that one, and you can't really see that he's green because that one isn't really green, but like some of them, like their subspecies usually are like green because they live in like forest areas and they adapted to like blend into their environment. I guess as like a survival tactic. They live usually in like tropical dry forest or like montane forest. They like anything with like shrubbery and things like that, and they usually just they'll like base their diets off of that. And originally I made like these four, but these are ugly, so like don't judge me. And like originally these are the ones I made, and this is like I labeled them in the back, and then there's a card in there to explain who they are. And then those are labeled with cards as well. But these are just examples of like how it is. But I didn't like these because they were flat and you couldn't really see how fat they were, like as birds. And like that's kind of like an important factor because that one's like really fat. So yeah. And then I just connected this to class because we did talk about evolution in class, but we didn't talk about it in the extent that I feel like it should be talked about, because I think that evolution is really important to just not only like the adaptations of humans and the adaptations of like animals and on Earth, but also like it's important to see how we evolve so that we can see like maybe like if we do ever find another civilization, maybe we can compare how like they evolved and like why they evolved in that manner. So
Thank you. Any questions?
Why did you choose Finchburg, like out of all that?
Because my project was on evolution, and Darwin, when he came up with theory of evolution, he was looking at the finches on the Galapagos Islands, and he was basing his theory off of like what he saw and like the transitions he saw in those finches.
I'm just curious, what are they made of?
Like, yeah, I molded them and then I tried feathering them to like make them look realistic, but it's way harder than you think it is. Yeah.
Any other questions? Can you describe a little of the process to make those?
Well, like for like the bigger birds or whatever, I actually had to like realize that like I can't like clay is like harder than you think it is to manipulate. And so I had to actually like take a cup of water and I had to like kind of like smoothen them out. So I would make their body and then I'd make their like head, and then I tried to see the shape of like their tails.
Mm-hmm.
Mm-hmm.
Are they to size? Or is that actually what?
Yeah, they're actually to size because this like at least like I want to think they're to size. I tried to make them to size so that like the fatter ones are the fatter ones. And I'm pretty sure like even if they got mixed up, you could like distinguish them by their beaks because their beaks aren't the same.
Mm-hmm.
So I'm trying to make their beaks as like close to like the picture as I could.
Okay. Any other questions? Okay. What's that?
Do I give this to you?
Hold it in the back for now. Yeah. Okay, Skylar.
That's big.
Illustrator.
So I haven't used one of these before. So it's just
Left, right, and then lasers at the top.
okay. So is it like an actual slides, or do you just have to scroll? Okay. actually works. Want to be my assistant? Sure. All right, just hold this up so I can see it. I just want to make sure I like stay on time. All right, keep this right. Good morning, everybody. My name is Skylar, and I did a presentation on Kepler 22b. And for my creative portion, I'm going to talk about the features that we predict about Kepler 22b that would make it sustainable for life. So to give you guys a roadmap of what I'm going to talk about today, it's going to be mainly about the features that we know about Kepler 22b and the Kepler 22 system, and then comparing it to ours. And then at the end, I'm going to give you guys my prediction of what kind of life we would expect to see on Kepler 22b. And then here's just so a NASA artist and scientist created this image. It's based off of the features that I'm going to talk about in a little bit, but that's what we think Kepler 22b would look like. So Kepler 22b is 600 light years away. For those of us who forgot, 1 light year is 5.9 quadrillion miles, so I would not recommend taking a Southwest flight to check this place out. And then it's currently in the inner part of the habitable zone of its system, which is up there. So see the blue ring. To give you guys a perspective of our solar system versus theirs, Earth is about 365-day orbit, and then Venus is 225 days. And then if you look at Kepler 22 Kepler 22b is kind of in between Venus and Earth, and it is estimated to be a 290-day orbit. Kepler 22b is assumed to be around 2.4 times the size of Earth, and that's, radius times the size of Earth is actually quite a bit bigger. So you can see it's in between Neptune and Earth, and give you guys, more of a size comparison. Neptune is just under 4 times the size of Earth. And then the next thing that scientists measured was the density of Kepler 22b, and just another refresher, Earth is 5.51 grams per centimeter cube, and then Neptune is 1.65, and we estimate Kepler 22b to be around 4.9 grams centimeter cubed. And I went into depth in my actual paper about how they determined this, but basically what they did is that they took a ternary diagram, which is a so just basically it's something that they just take a triangle like this, and they'll take like 3 different matters. So in this case, it was water, and then it was the mantle material, which is silicates and terrestrial planets, and then the core temperature, which was metals. And then they took the different types of radiuses that could be on the planet, and then Earth was So Earth was about here, which means it was like a bunch of silicates and metals with a little bit of water, and then based off of the densities and the increased volume of Kepler 22b, they believe for it to be about the same. So the big question is, are the conditions suitable for life? Based off of another calculation, which was the approximate average temperature of the planet, it took things involved such as the radius of the star, the reflection and absorption of the planet's surface, the semi-major axis of the planet, and then we pretty much determined that with similar greenhouse gases and albedo effect to Earth, Kepler 22b would have about a 71.3 degree Fahrenheit surface temperature, and then Earth's is 61 degrees. There is a little bit of uncertainty in this because we don't know the exact interstellar size, the mass, temperature of the sun. Of course, we also don't know the albedo exactly, so we don't know the atmosphere of Kepler 22b because it is really far away. So anything that wasn't, exactly defined, we just use Earth's as the thing. Yes, and last thing, liquid water is on the surface based off of, like I said, like this diagram that they determined. It kind of just like pinpoints the possibilities of there being different compositions of the planet, but based off of what we currently know and then how close it is to the star and relative to other planets. So 1 minute, okay. So finish up. There is a high chance of there being life on Kepler 22b. The last thing that I talked about was there being there's a time that the planet will be in the habitable zone of the star, and the star Kepler 22 is very similar to Earth. It's about 0.97 Earth radius and about 200 degree Kelvin less of the effective temperature. So since the planet is a little bit closer to Earth, it's roughly the same conditions. So my calculations, I did the astro.unl.edu simulation of what I just told you, and from beginning to end, there's about 12 galactic years of time that Kepler 22b will be inside of its habitable zone, and that would give it enough time for Earth, for Earth and Kepler 22b to have the same timeline. There would be multicellular organisms like by the end of its life. So yeah, that's my project.
At exactly 6 minutes.
Yeah, I had a timer.
Okay, all right, good. All right, any questions? We've got a couple minutes for questions.
You said it would be 12 galactic years in the.
So there's the habitable zone shifts. So if you had it on the outside of the habitable zone, like at the beginning, then you have it to where it is now, and like a little bit more. It was like 11.9 galactic years for when it would be outside of the habitable zone of the star. And then the Earth, it was 18 galactic years. It's like the birth of our sun. Like it's still in the habitable zone, but 12 years after 12 galactic years after the sun was formed, we had multicellular organisms with DNA material and stuff inside of it.
So I think maybe the question is, what is a galactic year?
Oh, a galactic year is 225 million years.
Ah, okay.
It's just a measurement that we had on the website.
Oh, okay. I thought those giga years. Like.
Oh god, actually it might have been giga years.
Well, no. Well, so if it's capital GYR, that's giga years, but
but
there is a galactic year that the sun takes to get around the
Ooh.
galaxy, which is about 250 million years. So make sure you know which is.
Oh lord.
Which is
Well,
which.
that certainly changes quite a bit of it. But I mean.
Andres?
How does Kepler 22 compare to our sun?
Kepler 22 is, like I said, so it's 0.97 sun radius, and then the temperature is 5518 Kelvin, and then our sun right now is 5,777. So it's. I don't know the age. Like when I did the simulation, that was it seemed like the sun that was Kepler 20, or the star that was Kepler 22 seemed a little bit older than ours, just based off of like how long it took for Kepler 22b to be in the habitable zone area that it is now. So, yeah.
Okay, thank you, Scott. Okay, Izzy, do you want to put your poem up now? Is that okay? Or do you want to just read it?
I have it in my slides. So.
Yes, all right, yeah, so you sent me slides, okay. So left, right, and laser. Okay.
Okay, so hi, my name is Izzy, and for my course project, I did a poem, but just so you can understand a little bit more about why my poem is the way it is, I have some information. So I did my poem on Europa, and it's one of Jupiter's moons. It was discovered by Galileo in 1610, and it has a really icy exterior, so scientists aren't sure if it's solid ice all the way through, or if possibly there's an ocean underneath. And since it's a moon of Jupiter, Jupiter's about 5 AU away from the sun, so it's well out of the habitable zone. But there's like, the activity it has with Jupiter could warm it enough that the middle is liquid, like a liquid ocean. So in 2013, this is why people might think there is a liquid ocean underneath the icy exterior. A water plume was detected on the surface of Europa by the Hubble Space Telescope, which means there might be possible breaks in the ice, which gives a greater possibility for life. Because if there's a break in the ice, then sunlight can get through, or more sunlight can get through. And just like on Earth, how there's life in hydrothermal vent systems, that could be possibly happening on Europa. And it also helped scientists to understand, get a further understanding of Europa's atmosphere, which is mostly oxygen and hydrogen. And these results were in a article by Lorenz Roth. But in 2014, more findings showed that the water plume may just be a result of a meteorite, because plasma, which is like a superheated gas, as it was described. The plasma detected in the atmosphere was not from Europa because there wasn't enough hydrogen compared to what they think the atmosphere should, compared to what they think like the amount of hydrogen should be in the atmosphere, there wasn't that much in the plasma. So they think it might be from somewhere else, which is why it might be from a meteorite, which shows that Europa is less tectonically active than they thought, which means life on Europa isn't likely. And these results were published by Szymanski. And so these results were by the Cassini ultraviolet imaging spectrograph, and these results were from the Hubble Space Telescope imaging. And Szymanski said that Roth's results aren't necessarily wrong, but there's data collection problems, and the data they might have gotten might have been from Io, which is I don't know if that's how it's spelled. Yeah, okay. And also there's just so much data because they're getting data from the Hubble Space Telescope, the Cassini, the Galileo, and the Voyager, and all that data together, like we heard from the SETI person the other day. There's just not enough resources to analyze all that data. And so because the articles kind of contradicted each other and there's so much still left in the open and there's no really conclusive decision, this is why I made my poem. So my poem can be read back and forth, like both ways, but Europa is full of ice, full of life. Europa, barren moon, it's not. As Roth depicted Europa, full of O2, O, and H, Szymanski illustrated Europa as not. Life could exist. There's no way Roth could be wrong. The atmosphere is perfect on Europa. It's not like Earth. Life could only grow in a place with the right conditions. Life needs tectonic activity, an atmosphere, liquid water. Necessary things missed Venus, Mercury, and Mars, unlike Europa, thriving with life. Earth is, but in Europa's ocean, life grows. It's impossible to think the water plume was a result of the meteor. Europa is geophysically active, as Roth says. The following statement is false. We will never find life on Europa. So in reading it from the bottom, we will never find life on Europa. The following statement is false. Europa is geophysically active, as Roth says. The water plume was a result of a meteor. It's impossible to think life grows in Europa's ocean, but Earth is thriving with life, unlike Europa. Unlike Europa, Venus, Mercury, and Mars miss necessary things, liquid and atmosphere, tectonic activity. Life needs a place with the right conditions. Life could only grow on Earth. It's not like the atmosphere is perfect on Europa. Roth could be wrong. There's no way life could exist. Szymanski illustrated Europa as not full of O2, O, and H, as Roth depicted Europa. Europa, barren moon. It's not full of life. Europa is full of ice.
Wow, that's awesome.
So these were my primary sources.
Okay, cool. Any questions? Yeah. Yeah.
How long did it take you to figure out?
It looked simple, but it took like 5 hours to configure it. And I finally thought I had it, but there were some parts where that's why it has to sound weird in some parts. Like I felt like Yoda talking backwards, but yeah, it was really fun to do though, to make it the accomplished product, saying it. I was
Yeah.
So is it supposed to be when you're reading it one way, you're optimistic, but then when you're reading it the other way,
one way was kind of supposed to be reading it like Roth. His article was kind of optimistic, meaning Europa it could be full of life and there's a great possibility, but then Szymanski came and his results showed that it's probably not full of life. So I wanted to incorporate that.
Yes, sir.
But don't both ways say at the end that there's basically no life on Europa?
Yeah, I guess. Yeah, but
But this preceded by a following statement is false.
Yeah.
But the following means the next one, right?
Yeah, so reading it this way, reading it front ways, the following statement is false, we will never find it.
Okay.
Yeah. And then reading it the other way.
Okay. Nice.
Any more questions? All right, thank you very much. That's really cool. Okay, Laura. You want me to show? You're doing the eulogies, right?
Yeah.
Okay. Do you want me to show them, or do you want to talk first?
Oh, you can show them because I'm gonna like read them out loud and then I speak. Okay. Good morning, everyone. My project was on the death of stars, but I also incorporated life of stars because my creative component was writing eulogies. So when I was doing this project, I've never written a eulogy before, so I read that you have to start from a person's birth and then life and then finally their death. So that is why I did research on how stars were formed and eventually like how they died. So my first eulogy is a eulogy of this giant star that no longer exists. I read an article or a report by Bali and Rupert that was called "When a Star Birth Meets a Star Death: A Shocking Encounter." So basically, what happened was that there was a star that once existed and it exploded through a supernova, and it was huge. So what happens is now that there are like little remnants left in space, but there's a nearby star that the remnants of the supernova can actually like eventually they're going to collide against each other, and that will leave possibility for a life of other stars. So here's my eulogy. Cephas flare, which is the remnants of the supernova. You were once a gigantic, bright, and blazing star. It was nuclear fusion that created you, but ultimately the end of nuclear process caused your destruction. You were a ball of chemical reactions, a compacted sphere of hydrogen and helium burning to the core. Physics and chemistry were working simultaneously to keep you alive. You were within a mass range of 10 to 20 solar masses, a condition that allowed for a creation of a supernova. Nuclear fusion released your energy that one day your outer layers started collapsing, which were able to create enough pressure to set up an explosion and push out dust material along with the luminous light that marked your end. If you happened to be 40 solar masses, your story would have been different. Instead of taking form into a dust cloud, you would have collapsed entirely within yourself and you would have become a black hole. But you were too small for that. Even though today you are a supernova remnant, you continue to make an impact on other stars out there in the universe. In about 1,000 years at a velocity of 300 kilometers per second, your lingering remains will collide against a B9.5 star nearby, and that impact will create many more stars. Therefore, your death does not signify an end, but instead a creation of new beginnings. So basically, what I read in this report was that let me just go back where we classify stars using the letters O, B, A, F, G, K, and M, ranging from the biggest to the smallest. So O's are really big, large stars, and they are also the hottest ones, and M's are the smallest. And just to give you kind of like an idea of how big these stars are, our star in our solar system is a G-size star. So yeah, they're huge because this star that once existed, in order to have created this supernova impact, must have been 10 to 20 solar masses. And I also included a part here where it says that if this star been 40 solar masses, it would have created a black hole, because the different stars have different outcomes depending on their sizes. And had it been 40 solar masses, it actually would have collided within itself, collapsed within itself, and became a black hole. And so essentially what I'm trying to say here is that like eventually, although it did die, it's going to create more stars. So the other eulogy that I wrote is for the sun in our solar system that eventually will also die out. And here it goes. You were born out of a cloud of dust that collapsed and collected neighboring material. Gravity pulled in condensed matter to the center. The cloud was able to spin and flatten out the cloud. Then you sprang about as the brightest object in the center. In our solar system, you contributed to the creation of life here on Earth. Every day you provided us with light, but unfortunately your life has not come to an end.
You're classified as a yellow dwarf, typical G-type star. Not too small, but not too big for us either. You were the perfect size. Your process of fusing hydrogen and helium did not last forever. One day you expanded and turned into a red giant star. Then you could no longer expand any further, and you collapsed and created a nebula. After this process, you were able to shine as a white dwarf, but eventually you ran out of light. So what happened essentially, or what we learned in class, is that the star was created through the solar nebular theory, which is like a cloud of gas and dust began to rotate, and then through the conservation of angular momentum, it was actually able to like spin the cloud and flatten it out, and then creating like the hottest object in the center. So that's like the birth of it. But eventually, what's going to happen to our star is that it's going to expand as it continues on, and then it's going to turn into a red giant star, and it's going to wipe out everything in its path, including Earth. So it's created us. It helped create us, but it's also going to destroy Earth one day. And then eventually, once that happens, it's gonna explode, and it's gonna just leave behind this little tiny white dwarf, which eventually will also run out of light, and that marks the end of it. Yeah.
Okay, thank you, Laura. Time for maybe one question. Go ahead, sir.
Okay, so it becomes a nebula after the
It's
red
like,
dwarf, or after the red giant,
like
and then
it leaves, yeah, like it leaves behind like little dust and clouds. So that's like the nebula part of it.
oh, and then the white dwarf.
Yeah, and
is
then
like
it's
the
just like in the
internal
center. Yeah.
part.
Okay, thank you, Stacey. Thank you, Laura. Next up is Stacey. Do you want me to show your poem?
No.
Okay.
Okay. Hi, I'm Stacey Molina. Basically my poem, I wrote a poem. I tried to write a poem. It's basically talks about two articles, well, 3 articles. 2 were talking about the original mission of Kepler's spacecraft, and the third one was talking about the new mission that NASA proposed in 2014. So basically, I'm just talking about like how the original mission and the switch to the new mission, which is still collecting data. So here's my poem. It's called Kepler's Original Mission to K2. Kepler's spacecraft, a spacecraft created to be sent into space to find a potential place in a habitable zone that has liquid water on its surface to serve a purpose, a key to sustain life, just like our planet Earth that rotates a star. That's so you know that planet's not too far. The planets that orbit a hot star make it easy to detect high surface temperatures that emit enough light. You know Kepler is there. Kepler had an original mission to analyze our galaxy of planets that rotate a star, not the whole galaxy, just one piece of it. A built-in photometer, 150,000 stars monitored, but not so successful. Only 1,000 exoplanets confirmed. You see, 6 years, this mission was so great. Scientists believed this was it, but 2014 came along. Scientists had enough. They wanted to expand the search. That's when Kepler's new missions came through. Scientists proposed a search for planets in habitable zones, not just in one area, but the ecliptic plane. An ecliptic plane is where the Earth is about the sun, a bigger range to search for life. They have not collected enough data. It's only been 1 year, but if you ask me, the new mission will only provide higher chances of life. If scientists find a planet containing liquid water, we may not just be alone. Any questions?
Any questions for Stacey? Can you go into a little more detail about why the mission changed?
Well, from what I read on the third article is that the Kepler's mission was just focused on one narrowed area, and scientists were like, we want to see if there's more planets and more like
potential habitable zones, like other expo planets. So they decided to change like where they were searching for life. They were not just focusing on one area. They wanted to explore like the ecliptic plane, which is more like area for them to search and stuff.
So there's one missing detail in there, in that the spacecraft broke
Oh yeah.
and it couldn't point in one spot anymore. So this is the plan that came up, and we certainly want to do it. But I think if the spacecraft hadn't broken, we probably should point in the same spot. Yeah. Yeah.
I was gonna ask what year was it launched?
Oh, it was launched March 9. No, March 6. March 6, 2009.
Thanks. Any other questions? Yeah.
When did it break down?
Huh?
When did it break down?
I didn't know about this.
About a year ago.
Yeah.
Okay. Thank you, Stacey.
Thanks.
Okay, I think that's it. So if you will please pass your papers over to that side of the tables, I will collect them. If you have any blanks, I'll collect them for Thursday. Great job, everyone, for staying on time, and we're even 5 minutes early because we lost a couple of presentations. But I look forward to Thursday's presentations as well. Thank you very much. If you brought an item, so that's the Finches and the game, and I've got the book. Please just leave them in the back table, and I'll collect them.
So you said that you're able to pull it up and see it on the projection screen?
Oh, actually, it might be. I will have to download it from here. So let's see. I can do it on my computer now, but you have a Prezi web account?
Yeah.
I think you have to set it up. So you should be able to share that with me through Prezi. There should be there's usually a little arrow that box the arrow going out, and you can put my email address on there, and I think that I should be able to see it. Then I can bring it up online. That would be easier.
Okay, yeah.
I will download the code. But just to be on the safe side, it would be good to just have a backup.
Okay, I'll do that.
Yes, ma'am.
I wasn't at the exoplanet lab. Can I turn that in for a mist? Or?
No, you have to be for the lab to be present for that.
Okay.
So, sorry.
That's it.
I had a number. I don't know.
So
Yes, sir.
sorry I didn't turn it in. It turns out n-body code is harder to initialize than I thought.
Okay. So you don't have any.
I'm working on it.
Okay.
I think I might use leapfrog code. That seems a little easier to get what I want. So yeah, once I have that done, I'll send it over.
Send it soon because you're presenting it on Thursday.
Yeah.
You have to show something.
I'll still work on the n-body code. I don't know. I have all the parameters right, and then when I run it, the sun starts to drift off to the side. Maybe it's how I'm initializing it because I have all the planets set up in a line on one side.
Yeah,
it might throw it off, but
maybe. But it's. The sun drifts. Does the entire system drift?
Yeah.
So what you should just do is just have a constant velocity offset. That's what you're missing.
Okay.
You're starting the sun with zero motion, and the
Yeah.
planets with some motion, but the sun has some motion that the planets are flying with. So you're not taking into account that this sun is already moving in some direction, probably down at this point.
Okay.
And so you have to have that initial velocity, but since you started rest, you basically shifted the whole simulation by some constant velocity. So that's why the sun is wandering.
Okay.
So I would just, if you wanted to show the planets going around the sun, you could just always correct to the sun motion.
Right.
Though that won't be quite correct, but I would say take an average of the sun's motion over the entire simulation and then just subtract that off.
Okay, cool. Thanks.
Yeah.
Some of my these things are in yellow. They're just yellow slipped papers because been
Oh, because you didn't have
bad
enough.
with that. Yeah.
Okay.
But so you keep the thingy?
For just for now, and I'll
For
just take a look
creating.
at it more closely.
Okay. Hey.
You'll get it back.
No, it's okay. It's fine. I was just thinking because I was like, I was going to take it now, and then because I have a game night that I was planning on playing it. So yeah,
That's like next 2 days.
Weekend.
Oh, okay. Yeah,
Yeah.
you'll get it back by
So,
Thursday.
Okay. Okay. Thank you.
No, I want you to play with it. It's cool.
I was really happy about making it because I was like, I could actually play this.
Mm-hmm.
Yeah, bye. Have a good day.
Thank you. You too.